I'm just gonna start. Thankfully, it's a lot earlier than usual. So I usually start like 11, 12 p.m. to a.m. Yes, and yeah, hopefully today I can just get over the remaining two. Yeah. So I guess first thing I do is make an energy drink. So we'll just you just I do have a I was kind of hearing this lecture, so I don't need to read this so much. And my assignment is also due tomorrow. I did part of it. I do have a lot of time here. Yeah, it's due in a day. I do have a lot of time left, so I still have like 4 hours to go, so hopefully I can do something in this much time. I mean, I do underestimate myself. I do. Here.
Post the announcements, but there will be a link that I will be sent to you. One of the students volunteered to hold a group WhatsApp where everyone can join to ask questions to each other. So if you want more notes or if you don't know how to compare proofs, then you can use that group chat to communicate with each other. Any questions?
Greenbelt. Are you hungry, but not that hungry? Try the new mini hamburger, or several, because good things come in small buns. Order now at Five Guys.
For the acute treatment of migraine with or without aura in adults, Nurtec ODT can provide relief in 2 hours, which can last up to 2 days. Don't take if allergic to Nurtec ODT. Allergic reactions can occur even days after use. Get help right away for trouble breathing, rash, swelling of face, mouth, tongue, or throat. High blood pressure and Raynaud's syndrome can occur. Get help for high blood pressure, numbness, coolness, pain, or color changes in fingers and toes. Common side effect is nausea. Ask your doctor about Nurtec ODT.
What is Nurtec ODT, rimegepant? Nurtec ODT orally disintegrating tablets is a prescription medicine that is used to treat migraine in adults. It is for the acute treatment of migraine attacks with or without aura and the preventive treatment of episodic migraine. It is not known if Nurtec ODT is safe and effective in children. Important safety information. Do not take Nurtec ODT if you are allergic to it or any of its ingredients. Before you take Nurtec ODT, tell your healthcare provider about all your medical conditions, including if you have high blood pressure, have circulation problems in your fingers and toes, have liver or kidney problems, are pregnant or plan to become pregnant, are breastfeeding or plan to breastfeed. Tell your healthcare provider about all the medicines you take, including prescription and over-the-counter medicines, vitamins, and herbal supplements. Nurtec ODT may cause serious side effects, including allergic reactions, including trouble breathing and rash. This can happen days after you take Nurtec ODT. Call your healthcare provider or get emergency help right away if you have swelling of the face, mouth, tongue, or throat, trouble breathing, or rash. This occurred in less than 1% of patients treated with Nurtec ODT. High blood pressure can worsen or occur after you take Nurtec ODT. Contact your healthcare provider if you have an increase in blood pressure. A circulation problem called Raynaud's phenomenon can worsen or occur after you take Nurtec ODT. This can lead to your fingers or toes feeling numb, cool, or painful, or changing
Let's try and do this. So, let's connect back to the. So sets are connected to. We go from chapter 1 that P of X is the open sentence. It becomes true or false once value is a substitute for X. We may define a set by writing This means that A is a set of all objects for set of object X for which P of X is true. Therefore, y if y is an A, then Py is true. Same way if Py is true, then y is an A. So this is 2.1. 2.1 is, I believe, basic set theory and set operations. So let's go to my textbook, I suppose. Here. So it's a basic concept of set theory. Then 2.2 is what? Okay, set operations. So basic set theory and set operations, like the. Uh, so what problems are we solving or set solving? In mathematics, we frequently want to talk about collections objects. All integers greater than 5, all students in the class, all solutions. So collection of objects, basically. And I suppose we're trying to prove it. A set gives us a precise way to describe such a collection. Well-defined means that for every object, we can determine whether it belongs to the collection. The objects inside a set are called its elements. Sets are connected directly to predicates. Recall in chapter 1 that, okay, I wrote this already. The universe matters, why we cannot create absolutely any sets. The empty set. The empty set is a set containing no elements. For example, for x in real numbers, x does not equal x, it's an empty set. Because every real number is equal to itself. There is no x for which x does not equal x is true. Be careful. Be careful. X is not in. We say that A is a subset of B. We say that A is a subset of B when every element of A is also an element of B. Symbolically, this states that for every x, if x is A, then x is in B. In Oriental language, whenever x belongs in A, it must also belong in B. That's pretty simple to answer. I see. So the theorem states the empty set is is a subset of A for every set A. But addition of subset we must prove for every x, if x is in the empty set, x also belongs in A. But x, but here x is in the empty set is always false. Therefore, the conditional if x is always true. Oh yeah, here because it's false. Because false, we don't really care what. So P implies Q. If P is always false, then it doesn't matter what this is. It's always going to be true. Equality in sets. The four major set constructions. AUB is for every x here, X is in A or X is in B. The unit contains everything belonging to at least one of the sets. Remember that mathematical OR is inclusive. An object may belong to both. Intersection, X is in A and X is in B. Okay, I kind of already know this stuff. Power set, which was this one's a little bit hard one. Okay, so this is a power set. So there's, I guess B is a set where B is a sorry, the B is a subset of A. So P is a set B where B is a subset of A, which is how hard it really is hard to but yeah, complements. Yeah, this is distributive. They're both distributive actually. So if A is a subset of B, A union C is a subset of B union C, and A intersect C is also a subset of A B intersect C. How the proofs in lecture work. Alright, sorry, I'm just reading this stuff out loud. But from everything I've seen so far, this essentially is just again like the tools. Like there's not really any examples. It's just telling us, well, the like the title kind of says it all. Basic set theory and set operations. It never really goes in depth into it here, which is, I guess, I would just pray that it's not enough. Better, but you don't know.
Okay, and what do you have to do? You need to prove that n plus 1 horses always have the same.
Oh, and also, let me see. Do I still have the quiz too? This was quiz 2, by the way, for it. Yeah, I got 100% on it for sure. So let x, y be an integer, sorry, be integers, and suppose that x is greater than 3. Prove that. Wait, sorry. Let x and y be integers, and suppose that x is greater than 3. Prove that x is not divisible by y or x. Uh, I'm just gonna pause the music for this one to try. I believe this one I kind of got this from just simple inspection. Like when I first saw it, I immediately got the answer. This one is pretty simple. It's basically just contradiction. Assume that this is rational, and then a squared over b squared equals 2. Then you show that a is even. So if a is even, then yeah. Sorry, I'll show you with my grayscope. Let x and y be integers. Suppose that x is greater than or equal to 3. Prove that x is not divisible by y, or x is not divisible by y plus 2. Um, I guess the question is how is that technically not possible? It could, right? I guess I'm thinking wrong. Is it x or this or that? I think I'm looking at this wrong because I did I'm pretty sure I got the question correct. But just to kind of just are they saying that x is not divisible by y, x is not divisible by y, or x is not divisible by y plus 2? S- So if x is divisible by y, so x is not divisible by y plus 2 for x greater than or equal to 3. Because the first thing that comes to my mind is like, let's say x is 4 and y is 2. Y is divisible, so y, so, 2 divides, wait, hold on. I think I'm getting mistaken, correct? Is it, indivisibility, is the y the greater term or the lesser term? I keep mixing that up. Okay, so yeah, y is the greater term. Okay, I think that's where I got, that's the, I understand. Because, yeah, if it was the other way where y is, like y does not divide x, or y plus 2 does not divide x, it would be false. But the other way, yeah, it's just, yeah, I completely understand now. It's simple. It's just basically they already kind of give us a hint here, which practically made the question like a 1 minute question. Funny enough, I actually got a bit stuck on problem two because I forgot how to prove it. Yeah. Okay. Sorry for wasting a lot of time this one.
Okay, let's name them 1, 2, 3, all the way to n plus 1. Okay, now what can we do? I'm going to first look at the first n horses.
This is okay, 2.1 and 2.2.
They have the same color by the inductive hypothesis. The last n horses, which is 2, 3, all the way to n plus 1, they have the same color by the inductive hypothesis, because they're still n horses. Therefore, 1 to all the way to n plus 1 have the same color, hence we are done. Where did we go wrong? Apparently I did see some horses that are more brown, I saw horses that are more orange. They definitely don't have the same color. Can anyone tell me where we went wrong?
Oh, so let me see. Let me see. So wait, there's only one horse in a group. They must only have the same color. Next, assuming that n horses always have the same color. And we need to prove that n plus 1 horses always have the same color. So let's name them 1, 2, 3, all the way to n plus 1. The first n horses 1 to n have the same color by inductive hypothesis. The last n horses 2, 3 by inductive hypothesis. Therefore, so where did we go wrong? Um, okay, so I think by interesting. That's an interesting conversation. I think about that one for a little bit. Um, so have the same color by inductive hypothesis. Inductive hypothesis, yes, that's true. I don't think so. Assume that n horses have the same color. Jeez, I feel like this is like a trick question. Let me. Still have not really have a thought here. No. Okay, I'll just say something stupid, I suppose. I'm gonna assume it's probably due to, I guess, the correlation between 1 and 2 is not really connected. There's no correlation. So here, because here have the same colors, here have the same colors, like the first N horses, the last N horses, there's no, wait, hold on. Actually, that's not true, because here it's saying that 1N, 1, 2N has the same colors, right? And 2, 2N. So because 2 is a subset, sorry, 2 is including both of them, that means it's essentially saying, yeah, yeah, yeah. So where's the, I guess, oh, it has to be the inductive hypothesis because I can't make an argument saying that horse 1 and horse 2 is, how do we claim that horse 1, horse 2 has the same color? By the inductive hypothesis. That's the root of the problem. So here we're assuming that N always have the same color. Yeah, I can't. It's hard to give an answer for this one. And she's a bit.
No, actually, step two was correct. Actually, the base step was where we had a problem. Okay, so instead of base case being two horses, um, it's just that the terminology, the group here, was not very clear. Technically, what you had to prove was that every group of one horse has the same color. But here we sort of like picked one group, and then we said that in that group, the horse will have the same color. Okay, so this was just plain words. You had to just make the statement much more rigorous. Or horses in every group have the same color is what we should have said. But because we hit all the details, something like this could happen. So don't worry too much about this. This was more of a food for thought. Um, and then you have to be very, very careful when you're forming a statement like this, is what I wanted you to see. Okay, so yeah. So we can talk about this at the end or in office hours. You're interested what went wrong, but don't worry too much about this. And the statements that we are going to deal with won't be as subtle as this one. Okay, any questions?
The base step should have shown that all
All group of
groups.
one horse have the same color, which is not true.
I see.
All right, let me start sharing the tablet screen. Give me just a moment. Um, Okay. Before we move on to step theory, I just wanted to see if you know the notation. So if I write something like this, does everyone know what this means?
Yes, we do.
Okay. Yeah. Let me just quickly write it down. So you first start by plugging in the 1 to an I. So that's 3 minus 2 plus 3 times 2 minus 2. And then 3 times 3 minus 2. In the next homework, you'll see some notations like this. So you should take a look at it. And in particular, you'll have some times where if you have sum from 1 to n plus 1, you'll need to divide this into 1 to n. And then plug in n plus 1 for the last term. All right, so I want to talk a little bit about basic set theory. Whenever you're doing logic, whenever you're doing proofs, and if you ever go into advanced mathematics, the fundamental language that we like to use are set theory. Okay, and if you haven't looked at set theory yet, then I recommend you to look at the appendix of the book. But as of today, whenever I see, say, set, it will be simply just a collection of stuff. We call it the well-defined objects. And I'll give you a few examples of what I mean by well-defined. Okay, so it's a collection of some objects. And then usually the way that you write this down is as follows. Let's say you have a set A. We usually write down the set as capital alphabet. And then we're going to give a name to the objects inside. Let's call it X. And then you're going to put some open sentence like this. Okay. So what this means is that something is going to be a object inside a set, or we call it an element inside a set, if and only if you plug in y to your open sentence, this is true. Okay, so it's basically a different word of saying that this is the true set of the open sentence px. Okay, so let me give you an actual example. So we have an x, and my open sentence is that it has to be inside the integers, and then x squared is less or equal to 9. Okay, so now this is how the book writes it, which I agree why they do it like this. But to save some space, oftentimes I'll simply write down x is inside the integers, and then x squared is less or equal to 9. Okay, and maybe for 20 or 30 seconds, think of what kind of elements can be inside B. So that will be 1. This is not a full list though. Yes. Okay, so yes, you'll have integers between -3 and 3. Okay, so you'll oftentimes write something like 3 is inside B, or -2 is inside B, and then 4 is not inside B. Okay, how about this guy? I don't want to give it a name. It's all the x's, such that x is not equal to x. So of course, if you are not yourself, then that would destroy the world. So there is no such element. So oftentimes, we also denote it this way, meaning that there's nothing inside. Okay, and then there's a special notation for this. You write down a little
Yeah,
circle,
we kind of
and
saw
then
that at
a
the.
diagonal line. Okay, and this is called the empty set. Okay, and then it is sort of an axiom that this is also a set. So by axiom, if you get nothing, collection of nothing is still a set.
I see.
So what can we say about this? For anything that exists, x is not going to be inside the empty set. Pretty cool.
It's moving day. That's right. Mint Mobile is.
Okay.
If you'll have it.
Okay. Now let's again look at a pretty interesting example. If you're into math, then you might have seen this example before. Okay, now I'm going to define A.
Probably the
Set.
Russell paradox, I'm assuming.
and then I'm going to call the element B. Now I have a question to you. Is A an element of A? In other words, is A inside A?
I kind of feel bad because she's always
Okay,
like
so let's see how this goes.
basically quiet
Number
in like
one.
a corner, like wait for someone to respond, but no one's responding.
Okay, so let's see how this goes.
Yeah,
Number one.
I typically don't
So let's
attend
assume
classes
that I
because
believe that A is not inside A.
it's like early in the morning, like at 9. I don't really wake up at 9. I wake up at like at 7 p.m.
So I tried to prove using contradiction. So I tried to prove that A is inside A because
I
I
should
want
be
to
in
say that
classes
A
though.
is not inside A. Okay, but if I say A is inside A, then A has to satisfy this. Then A does have a property that is not inside itself. Okay, but we have both things at the same time. So this is a contradiction. Okay, so as I thought, A is not inside A. Okay, but we get into a problem because if A is not inside A, then that makes this open sentence true. Therefore, A must be inside A. Once again, A is inside A is not inside A, so this is a contradiction. Wow, did we just break math? And then, actually, this was done by a mathematician called Russell, and this is called the Russell's paradox. And when it first came out, it did break the math that they
Not to be offensive, but okay, I'm not. Never mind. I'm not gonna say it.
knew at the time, because they did not have an idea how to fix this. So the solution that they came out after looking at this weird example is that they realized that you might not have a set of all sets. Okay? So whenever you're doing set theory, most of the times you can just think of set as collection of some objects, and you will run into no problems. But if you extend that idea and then
All right, bye bye. I just gotta do something. can't really handle the consequences of yelling at a guy, but she wants to be a guy. The point is, she can't handle the consequences because they're not gonna punch you in the face and shoot you. I mean, the thing is, she can't handle the consequences. She can't handle the pressure. The thing is, she can't handle the pressure. She can't handle the consequences. Whereas a guy can. A dude smaller than me is not gonna yell like that. A dude smaller than me, so a woman can't. So a woman can't because she's a woman. I'm just saying, a man can handle the pressure. A woman can't. Because when a woman wants to handle it, I mean, I gotta put this in question though. But she's not a man though. But she's not a man though. It poses a question. I mean, it kind of poses a question whether she can do it alone or not.
try to abuse it, like, oh yeah, I mean, set is an object.
Sorry for wasting
So maybe
time.
you can
I
just look
was
at set of
literally
offsets,
just on my
and then
chair,
things
just sitting down
break
because I
into hell.
didn't have motivation to
So
start the
just
video. Sorry.
recognize that in abstract mathematics,
I guess
whenever you're
it's
talking about sets,
yeah,
it's not just a
that's
collection
the
of
biggest
any
obstacle I
objects.
have.
You need
Is
some
just that
standards, which we're not going to talk about.
handling
It's
how
rather too
to
complicated for this
like
course.
just find the motivation
Okay.
to start
So the
things,
only offset that I wanted to
especially when you
add
don't
from this
want to do it.
example is that not all px, the open sentence, defines a set.
But yeah,
And
enough
you
with
won't
the
have to worry about which one makes a set or not. Just know
sentimental
that there
stuff.
are some sentences
Let's do
that is not
this.
going to give you a set. Any questions?
So here,
Okay. And if you like to think about this a little bit more, here is another version. Try to see if this sentence is true or false. So because of this example, what people decide to do is that whenever you're talking about a set,
yeah.
it's better to first
Okay,
set
so
aside,
he does give some examples as a set theory. Sorry, set notations.
and call it U
But um,
or the universe,
wait. Now I think about it,
and our set A must be part of the
here
universe.
in the second page,
So whenever you look at a statement like this,
here sanitation is
this is bad
part of 2 points. No.
because I don't know where X comes from. So
But
instead,
sanitation just simply
write
just there. It stays here, I
X is an
suppose.
integer, and then X is less than 2, less or equal to 2. Or if you want a different universe,
I believe this
then
is 2.1 to
specify,
2.2,
and then
which
say that
I
X is less or equal
guess
to. Any questions?
it's like I'm halfway there, but I'm like I can't really find it in me to just like pay attention.
Okay. Then let's maybe summarize several important concepts from set theory.
Please.
Okay, so if you have two different sets, I want to see which one is bigger. And we write this notation over here. It's a little elongated C with one more line. Or if you like, you can not write that line. This is A is a subset of B, and this happens whenever you can show for all X, oftentimes inside the universe. If X is in A, then X has to be also inside B. And you should think of this as A being completely inside the set. Okay. And then we're going to say that the two sets are equal to each other. Okay. Then this is the same thing as saying that A is inside B and B is inside A. Okay. So think of it, I usually think of it this way. A subset is if and then statement. Okay. And then equality is equivalent sentence. So you need both A is inside B and then B is inside A. Okay. Now using this definition, let's see what kind of proofs we do. So my first example is to show that an empty set is a subset of every set A. Okay, so let's use the definition. So we want to show that for all X, we want to show for all X, X is inside A, the empty set, then X is inside A. It's true. How do we show this?
Oh, that's yeah. It kind of show this since
Any ideas?
it seems like the summary kind of covered everything here. So thank God for the summary.
P implies Q is going to be O, such that X.
Then this is like yeah, union and then set differences, power set.
Of everything we think is the union P intersects C, and that's exactly the right answer.
So here is like ANC, right? ANC and then BNC, correct? So obviously, A is a subset. Sorry, here since C is also an element in A. Sorry, this set right here, where yeah, okay, I see how this is true. Yeah, basically, essentially this right here. But yeah, I kind of skim through this because it doesn't seem something that's like unusual supposedly.
So let me begin. This will be lecture.
So I just want to recap. Let's recap this a little bit. Where the problem we're solving is we want to generalize a group of objects, collection of, like basically to talk about a collection of objects. Talk about collection of objects, and when we do so, we want to find, I guess, notations as to how hmm, we can represent them, I suppose, and also find ways to make arguments and statements about them too. I guess, did this topic really preface? Let's talk about some theories as well, but he never really prefaced how to prove them, correct? Like they're like I don't think it really, unless I'm mistaken, right? It just simply talks about the set. Like if X is this, yeah, I kind of figured. So I don't see any type of proof at all. I mean, I guess it does when like stating that like X X is a notation. Sorry, X is an empty set. Sorry. For every power set, there's an empty set included. Or yeah, right.
That feeling when you check your bank account and your paycheck's days away. And of
There is some aspects of proving towards it, but finally, it downloads really fast now. Okay, so I do should I want to start doing my homework maybe. Wait, what? S- Yeah, it's the homework. Let's go here. Here's the homework. I've done relatively, like, I think I've done all the way up to C here, I believe. So D is, sorry, problem 4, not 1 to 3, sorry. I don't know much about this aspect of relations. S- I I believe I made a mistake here. No, one of these questions I made a mistake, I believe. Yeah, I watched one of my previous videos and I saw a mistake I did here, I think. I haven't done this 1B problem too. This direct proof is not gonna be easy. But let me just see. Is there anything I can relatively do? This one, I guess this topics, problem 3 and 4 talks about it's more on set theory, or the 2.1, 2. This kind of touches on those. Or I think problem 5 it does as well. It seems.
Granger makes it easy to find and order the products your team depends on around the clock. Because when boxes are packed, pallets are stacked, and trucks are waiting at the dock, the last thing you want is to run short on the supplies that keep your warehouse moving. Granger is there to help make sure nothing runs out when shipments are rolling out. Call 1-800-GRANGER, click Granger.com, or just stop by. Granger, for the ones who get it done.
that's not your thing, right?
Really, as a designer, that is not within my field.
Martine, your business is thriving. Why don't we test how Intuit Intelligence can help you grow even more confidently?
Let's do it.
Are your expenses higher than last quarter?
I'm not sure.
Want to check with Intuit Intelligence?
Definitely.
Look at that. Real-time personalized insights showing where your money is going and where it can grow. That's QuickBooks showing up as your perfect partner.
It is indeed.
You're crushing it, man.
Nice to be here. To be a part of any of this. I was just sort of Discount Furniture has the furniture you've waited 250 years for. We've got power reclining sofas as low as $7.99, five-piece dining sets as low as $3.99, Bobo-pedic mattresses for as low as $2.99, and of course feature-packed bestsellers like my Playday sectional with pop-up sleeper sofa. So stop in or shop mybobs.com to see where America shops for furniture. Oh my Bob!
Bob's Discount Furniture.
Okay, so let me see. I let me kind of. Okay, so for problem 4 and 5 and seam 6 too, I guess should I just start doing or take notes? It's due tomorrow, so like I have still like a lot of time left. I guess today I should probably do. I think I did 4A already, but just put my force onto it. Maybe 5, 6, and 7, and maybe 8. No, 5, 6, 7, and then 8, 9, 10. I can do it tomorrow. There's the recommended problems I should do. But man, look at this. So yeah, I should probably do 5, 6, 7, and maybe try doing this again. I still don't have a clue how to approach this. So when I say direct proof, it just means that like given this equation, given its expression, show it it's divisible. So show that I gotta show it's like it's a multiple of 4. Wait, I think I know. So um, let's zoom up close. So we can remove 1 7, so it could be 7n minus 1. Since it's positive, that means that there at least has to be at least plus 1, right? So we can do 7n minus 1. So this will be 42, I believe, right? 42? No, no. 6 times 7 is 42. That means no, 42 is not divisible by 4. I'll have to go to TA and ask this question though. Also, this one too is where I'm question. Well, yeah, this one here. I believe this is true, correct? If wait, give me one. Yeah, this should be true since. But yeah, I'm gonna revise these just to make sure they're correct. Yeah, I'm wasting time talking and not solving. So 3.1, which is this lecture right here. So what problem are relations trying to solve? So one person is a parent of another. One account follows another account. An animal lives in the habitat. One number is less than or equal to another number. So a relation is simply a collection of connections that we decide are true. So for example, suppose A is horse, frog, and fish, and B is land and water. A possible lives in relation is R, host land, frog water, fish water. The ordered pair frog water is in a relation. That is true. Okay, so it seems that this R right here, this relation is a set. I still don't have it's still a bit hard to explain what relation means. So I'll just look up here. Relation math. So a relation in mathematics, or how about, let's type logic. No, wait, math logic, I'm stupid. Or discrete math, if you will. So a mathematical proof for a relation is typically shows if it's reflective. Okay, that's equivalence relationship. Wow, I'm surprised I actually know that. Wow. Um, no, 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 no. Here. Okay, so here, relation in mathematics. A relation in mathematics is defined as a relationship between two sets. If we're given two sets A and B, and set A has a relationship with set B, then each value of set A is related to a value of set B through some unique relation. Here, set A is called domain of relationship, and set B is called the range of relationships. Oh, hence, okay, so that's what makes sense. So in total, there's going to be 6 elements. No, not really, because it's okay. There's going to be more than so. Basically, it's going to be either A and more, right? Because since each element has to be related to B, horse, frog, fish. So example, suppose there are two sets X and Y. A relationship R states that X, Y is in relation R if X is a square of Y. It can be represented using ordered pairs. So let me see, X is in a relationship. If X is a square of Y, okay, if X is a square of Y, okay, I see. So yes, X is a square of Y. So yes, 2 times, so negative 2 is off the square of 4. 2 to the square of 4. Negative 6 to the square of 3. 6 to the square of 3. And as such, this is actually a domain though. So I was wrong. The length of the set of the length of, sorry, the size of the relationship is not sorry, it's not going to be always x. Okay. Finite automata. I remember doing this. I think I have a video on this, but it's some stupid video which not worth even discussing. It's just kind of sad to see that my whole college experience was practically me behind the screen, just complaining about how negative my life is. Yeah, you should not dwindle, shouldn't complain, but I just realized like it's just same as high school. Nothing really changed. Okay, so this is what we're trying to solve. Now, Cartesian products is all possible connections, which I know, yeah. It's basically going to be the, so 3 to the power 2, I believe, right? No, 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 no. Wait, yes. So it's gonna be do, 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 do. So, okay, so it's gonna be 2 to the power 3. No, no, no. Am I stupid? I think it's 6. Because horse is gonna be 2. So it's 3 times 2. So why is it powered? Okay. So talk on the next subtopic is Cartesian products. Every possible pair are only the pairs that satisfy a relationship. And R is a subset of the Cartesian product. Ordered pair are ordered. In general, the ordered pair A B is not the same as BA. For example, horse land makes sense for lives in, but land horse would mean that land lives in a horse. So, okay, third topic, Cartesian products and set operations. That looks ugly. That looks really ugly. Intersection, union. This is, again, like, what I'm trying to say, it's yes, that is the right way to read this lecture. Are mostly building a language and toolkit for set theory rather than introducing a completely new proof method. The lecture spends most of the time defining set operations and operations such as these such as to. So the main goal is learn what sets mean, how the notation works, which properties are available for later proofs. The actual proof skills come from chapter 1. Set notation simply gives those proof and method a new subject to operate on. Therefore, proving a subset statement is just a direct proof of a conditional. Taught how to prove. Section 2 teaches what set statements are. Essentially, it's a good way to put it. union. Okay, so what is a relation? A relation from A to B is any subset of the Cartesian product. If A B is in R, we write A R B. This is read as A is R related to B. Example, the relation the relation the relationship less than or equal to on R is so R is a set of elements where the pair AB is in or sorry is are real numbers where A is greater than or equal to B. Therefore, 2 is R related to 4 because 2 is less than or equal to 4, but 5 is. Wait, let me see. What the hell is this notation is weird. I'm guessing it's like a equal, like not equal sign, but the slash was made differently. Okay. Okay. So it's R. This means R related, not R related, but okay. So this is defining what a relation is. Here, what does your relationship on A mean? So this is an important wording distinction. A relationship from A to B satisfy, yes. A relationship on A satisfy R, R being a subset of A, the Cartesian product A and A, which is just okay. Um, Important clarification: a relationship on it does not mean that every pair must be included. It only means that every pair that is included must have both coordinates in A. For example, let A equals 1, 2, 3, and R is the pair 1, 1, 1, 2, 3, 2, which obviously includes satisfy that R is a subset of A because the pair 1, 2 is also is a subset of the Cartesian product of A and A. Like there's 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, then 3, 1, 3, 2, 3, 3. This is a relationship on A, even though pairs such as 2, 1 and 3, 3 are not in. Wait, even though pairs such as are not in R. I thought I was gonna say are not in A, are not AA. Okay, I'm kind of speaking through this. Hopefully, again, it really comes down to the notes I'm due on this. In programming language, for every pair x, y in R, x must be in A, y must be in A. We are not saying every possible pair x, y from A must be in R. A relationship can be represented by arrows. So arrow diagrams here is talking about relationship about A means, and now we're talking about what is relation. I guess also I should kind of question what does this even have to do with proof? Again, this one just looks like we're just simply talking about just defining relationships, relations. It's like another toolkit. We have to like later on. We have to later on see like why does this have to do with and let me see what the book kind of says here. So we're in 3.1. This is in order relations and modular arithmetic, which modular arithmetic is going to be in concepts of. So yeah, it seems that later on these tools I suppose is going to be okay. This is an identity relation where it's just the set where AA is going to be A. So it has to be both. So I'm gonna assume IA is also a subset of the obviously it's a subset of the Cartesian product of AA of A. So A times A. Inverse if R is a relation of from A to B, then the inverse of R is B A where B sorry where the order sorry where the order pair of BA is in the Cartesian product B, where A B. Okay, okay, um, okay. That's So this is just inverse, which we haven't touched on in the last chapter 3.2, I believe. Yeah, 3.2 is what this is where we ended, and next chapter is gonna be 3.5, which I haven't. I'm gonna do, I guess after it's 10 right now. I'm gonna do this after. So okay, so this is inverse. We're talking about inverse here. Now, domain and range, which is part of my part of my homework problems. So domain and range. A relationship does not necessarily use every element of A or B. The domain of contains of all first coordinates that actually appear. So domain of R is um, the set of elements where X is an element of A, is X is in A, and there exists a Y in B such that okay, so there exists a Y in B such that X is related to Y. Um, so again, the set of all elements in A. So every single element in the domain of R is elements only in A. Okay. So the range is okay. So this all kind of correlates to this. It's strictly X is related to Y. So here the first current ACD. So domain of E. Oh here. Sorry. Why is E also don't know why. So domain of E here is A C D. But with the how do we know what the relation is though? There's no wait. I thought the relation has to be. So how do we know what the interesting? Um. Wait. So this is again. I just want to make things a lot more clear. So okay. Wait. Hold on for a second. E is a relation. E is a relation. Sorry. I was under the interpretation that E was like simply like a random set, which no, E is a, and I should have known this because it's given order pairs. So yes, this is essentially saying that A is an element of Y. What is it? A let A equal X and B equal Y. A is related to B and A is related to C. A is related to E. So given this, A this right here is in the subs to set A, and B, which is Y in a sense, is also is in, and it also exists. So yes, I understand now. So 10, composition of relations. Two composition joins two relationships together. Suppose R is a subset of the Cartesian product of A and B, and S is a subset of the Cartesian product of B and C. The composition S of R is a relationship from A to C. Okay, shoot. Okay, composition is kind of a tricky one, isn't it? I still have the lecture, so thankfully I can after. So composition is where I'm pretty weak on. Wow. What the actual damn. For each A and A, for each B and B, if A and B is an R, for each C and C, if B and C is an S, add AC to Okay, this composition makes a lot of sense. The relation defines R1 as where y is equal to the square root of x. Essentially here, where R1 follows R2. Composition is generally not commutative, so the composition of R1 and R2, I'm pretty sure, is not the same as R2 follows R1. Relative versus function. Hardest part is to watch out for is no, the confusing part is definitely composition for sure. Okay.
Number 7.
The relationship is a selective
7:22.
word pairs.
And I don't have a particular announcements for today, so I'll wait 30 seconds to see if you have any general questions. And if not, I will start talking about relations.
I'm here. I guess I can stop here
Alright.
and then
As I said
finish.
before, if you can,
I
just
should probably
use
do
the
5,
raise
6,
your
7.
hand button. Before.
I should probably aim for doing every single problem, but I'm just a bit too concerned on because this one. Okay, so yeah, this is basically 3.1. Oh, okay, finding R1 isn't super difficult. So finding A, B, and C, then D is a little bit okay. D is a bit annoying. No, not really. C and D, it all comes down to here. So RB relation from A to B and SB relation from B to C. Prove that. Demonstrate that the domain of S follows R is maybe false. Equal. Okay, equal. Prove given relationships are equivalent relations and find the requested class. But this is interesting. Oh, it's equivalent. It's equivalent relations. No, okay, that's why I was confused.
For the extra questions, so that I can wait.
But yeah,
Alright,
I
so
think I could do
this is
5,
I think
6,
one of
and
the important
7 for
concepts
sure.
you get into
5 and
abstract
6 will be a
mathematics.
bit
And then
annoying
relations
since
are
I'm
literally
not
relations as if you're using in real life.
precisely
So a
good on
non-mathematical
relations right now.
example of relations are
But
something
it's
like
doable, I suppose,
is
right?
a parent of.
With practice.
Okay, so Alice is a parent of Bob, or I am not very good with celebrities, so yeah, I want to give like a celebrity example, but I can't. So that is an example, or follows on Instagram could be a relation. So person A is following Instagram on person B, and maybe we can also do something like lives in. So for example, horse lives in land, dragons usually live in our minds, and so on. Okay. So for each of these relations, you always have something on the left and something on the right. So for the first one, you can think of this as a relation between person to person. And for the second one, you can maybe think of it as person is following on Instagram's account. And in third example, I will think of like animals and pets. So an example of the third one is that my set A will be a certain list of animals. So let's say horses, a unicorn, a dragon, frog, and fish. And then set B, it will be some list of places to live, habitats. Let's think about land, water, and air. Then your relation is just an arrow, where maybe I'll do an arrow from horse to land. The horse usually lives on land. Unicorn, that's imaginary. Dragon is also imaginary. Frog can live in both land and water. And then fish lives in the water. So this will be a example of a relation. Let me give you just a few more examples before defining what they are. Let me write down a few mathematical examples. So inequality, like y is less than x is less than y, is a relation between numbers. Equations, like y is equal to x squared, is going to be a relation later. We're going to somehow think of functions as relation. And then if you're talking about between two lines, maybe something like is parallel to or intersects can be a relationship between lines, because if I see two lines that intersect, then we say that they intersect. And then if they don't, then there is no relation between those two lines. Any questions so far?
Ever wish you had a buddy who totally understands all your gaming moments?
Thank you.
Kako
So
your
here,
tailor-made-
instead of drawing arrows, we would like to write it in the following form.
Okay.
So you always have a starting point
This
and then
kind
the
of is
ending
what
point.
the
So we'll write our relation
summary was
as
talking
a
about.
pair, or to be more specific, ordered pair. So the star over here.
I should say
we'll
though that
oftentimes write it as
I am relatively
set of pairs, horse to land, okay. Frog, land,
super naive when it
frog,
comes to
water, and then
set
fish
relations
and
with set theories right now. Even set theory and set
and I need somewhere.
properties. Yeah,
all
I'm
of this
super
are
big on
living
this
it.
stuff.
So here comes the following
I still need
definition.
to make sure I'm
So if
solidified
you have a
when it
set A
comes
and
to
B,
stuff. And hopefully, since our exam is on Friday,
we're
I
going to
should be
define the
solidified by
product.
this by definitely by
Or
tomorrow. So I should be
like a Cartesian product, because there are different types of products.
Unfortunately, I'm gonna be like doing.
Set theory. Okay.
I noticed that 12-hour studying sessions are
And this
really
is defined as the following:
unproductive.
A times B,
You tend to fall off.
which is basically just ordered pair.
Unless you
A
take
and
like
B,
a
where A is
huge
from A,
huge
and then the second B is from the second set.
dose of caffeine. It's relatively going to
again,
be
if we go back to
incredibly
this example,
unproductive because I'm going to
if
forget
you
a
want
lot
to
of
figure out
stuff
what A
too.
times B is, this is going to be list of all the pairs that you can think of, where the first coordinate has to be from this set, and then the second coordinate has to be from this set. So what you'll get is horse, land, horse, water, horse, air. Okay. And you'll do this for unicorn, land, unicorn, Cartesian product, A times B. Okay. And relation is basically just going to be a sub-collection of this ordered pair. So actually that's exactly the definition. Relation from set A to set B will be any sub-collection of elements from A times B, and then that sub-collection will somehow give you the relation between things from A and things from B. Alright, and A times B is all the possible pairs that you can make from set A and set B. Now, before I move on, I wanted to give some warning. Oh, I'm going to write down the definition again, but I want to say one more thing about...
Yeah. What the actual fuck?
So A times B intersects C times D. And then A times B union C times D. imagine if you haven't worked with this before. But A times B, you have all the pairs, everything from A in the first coordinate, and then everything in B for the second coordinate. And then the second one, C and D. So if you think about it, the only interaction that can happen is between the first coordinates, and then only thing that happens between the second coordinate is between B and D. So as Saki said, in order to be both of them, the first one has to come from both A and C. And then the second coordinate has to also come from both B and D. So that's exactly correct. If you intersect the two products, then it's going to be the intersect of the first coordinate times the intersect of the second coordinate. Logging in again, yeah. Great. And C times D is going to be 2 comma. Right? Okay. Now, if you take the union of these two, okay, then you only get 1 comma 1 and 2 comma 2. On the other hand, if I do A union C times B union D, A union C is 1, 2. B union D is also 1, 1, 2. So you have 2 choices for the first coordinate, 2 choices for the second coordinate. So this will be 1, 1, 1, 2, 2, 1.
Yeah, all this
stuff
self-explanatory.
So you definitely get much more elements inside the second case than the first. So yeah, intersection, they work nicely. But for the union, doing union first gives you much more choice in your first coordinate and then the second coordinate. So if you increase the number of choices first and then take the product, you'll get much more than taking the product and then doing the union. And then if you think about it in numbers, it makes total sense. 1 times 1 plus 1 times 1 is 2. 1 plus 1 times 1 plus 1 is 4. So oftentimes the one on the right is much bigger. Any questions? Okay, let's precisely define the relation between two sets. So once again, A and B are sets. Okay. Then a relation is also a set. We usually denote it as R because it's relation. Is simply going to be, So a relationship R, we love to specify, so this is from A to B, is just a subset of A times B. Okay. And sometimes if A and B are the same, we simply say the relation is on R. On A. Okay. And this is a set of pairs, so we'll often write this down. Then we will say A is R related to
B.
B, or simply related to B, and also write A R Okay, why do you want to introduce this notation over here, ARB? It's because I think the most natural relations to talk about is less or equal to. And then this will be a relation on R. Now everyone knows what this means, but let's try to use the definition. Okay, so this is going to be a subset of real numbers times the real numbers. Okay, so it has to be a pair inside R times R. And then when are they inside less or equal to? They'll be inside less or equal to if they are, if the first element is less or equal to B. Okay. And then now, if we use this notation, we can simply write down A is A comma B is inside less or equal to, if and only if A is less or equal to. Yeah, and I know this is like a horrible thing to write down because everything looks the same. But this is the motivation why we want to use this notation, AR. Let's see, what other do I want to do? Let's do one more example. Um, let's look at R. Again, relation on R. And then later on, the most important relation that we're going to look at is going to be functions. Okay? So let's, if given a function, you can define a relation inside R times R. Okay? And how do you define the relation? It's going to be inside there if y is equal to, let's say, x squared. Okay? And there's nothing to check. This is indeed a subset of R times R, so it's going to be a relation. Okay? And then we'll write something like 2 is related to 4, because 2 squared is equal to 4. But 3 is not going to be related to 7.
There you go. Yeah, I figured she wanted to do that, or yeah, not related as in slash R. Okay.
Nothing too crazy, right?
Not yet, I guess. So I guess the plan now is to do questions 5, 6, and 7, then look at 3.5, and then go to the gym afterwards.
Yeah.
Hopefully by then I should wake up at 8 a.m. I have to drink my protein shakes, however,
I was
which
thinking if there's any
they
other
taste like
interesting
crap,
examples
honestly.
that I didn't prepare. Yeah, no, I'd like to think of this example also. So there is a field in called group theory, graph theory. And then what they're basically doing is they're looking at relationships between us, or like they're looking at connectivities and then trying to make relationship between them more natural. So they study like this dot, and then arrows between them. Okay. So let's name them. And then oftentimes when you're doing the internet, you think of internet as a graph. So this is a web page you visit, and then whenever there is a link between them, if you have a link from A to B, you draw an arrow. So you should think of the internet as a gigantic graph. And a graph is a relation. So how is it a relation? That's called V. That stands for vertices. And those are these points. And then a graph can be represented as a relation. Let's call it E. A relation on V. And E is going to be basically the arrows. So we have AB, AC, AE. So that covers these 3 arrows. CD, and then DE. So I think this is a pretty fun example to keep in mind. And then whenever you get into applying linear algebra to this, then you will be able to do a lot of different things. So that's one example. And here is a very trivial example, but it's important. We call this the identity relation. So here, I'm going to use capital I, A. And then this is just the collection of things, where the first coordinate and then the second coordinates are the same. Or, I also like to think A and B inside A times A, such that A is equal to B. Right, any questions so far? Okay. Now, given a relation, let's say from A to B, similarly to a matrix, if you know, we can think about its inverse. So it's going to be all the pairs, where you just literally swap x and y, and then that should be inside R. And this is called the inverse relation.
Yeah, most of this stuff has already been covered.
If we have a relation from A to B, we want to reverse this relation, so it's called the inverse relation.
So
this
x, y, where
from B to A,
y is less than 3x minus 4. Oh, so find relation of.
Okay. So this is a pair such that x plus 4 is equal to 3y. If you move over the minus 4, divide both sides by 3. And then maybe if you really want to, you can switch the order. Say y is greater than x plus 4 over.
Same thing?
Now let's just do two more like quick fun stuff. If our relation R is a parent of, what will be its inverse relation? And one more. If R is sibling of, then what will be its inverse? Anyone?
Would the first one be has parent?
So let's say like Alice is a parent of Bob. Then what is Bob of Alice?
Wouldn't it be the child?
It's
the child of?
Yes. And for the second one,
A sibling of?
so this one, the inverse would be the same as the original. Okay. And next time, we're going to give this a special name. This is called symmetry because R is the same as R inverse. And if you think of in terms of arrows, if you can go from A to B, then you can automatically go from B to B. Okay, so yeah, maybe I'll use this example. So if you see over here, if you go back to this relation, our V has A, B, C, D, E. But if you look at the first coordinate, B and E were never used as the first coordinate. And then if you look at the second coordinate, D, E, A was never used. Okay. So in a general relation, some of the elements might not be used. So I want to give them a special name. So this is where this domain and range first came into place. So a domain of this E
Let's see.
will be all the possible first coordinates. Okay. So in this case, A, C, D. Okay. And then range is going to be all the possible second coordinates. In this case, it is A, C, D. And they are most of the times not the same thing as A and B. So let me give you also a precise definition because in the homework you will prove that the domain or the range of some relation is this. And then in order to actually prove it, this definition will be hard to work with.
With a swarm of hungry mosquitoes buzzing around.
And this is
then you might have Insuranoia. And if you have Insuranoia, then you should get NJM.
D is ABC.
They go to great lengths to do what's best for their policyholders.
Happening.
No jingles or
starting from what?
Just great insurance.
It's probably not a good idea, but I'm probably gonna skim through this.
I can go to.
What's your answer?
How about I should stop here since it's already 11?
A shoe? A toaster?
Nope. Yes,
I have like 20 minutes, not even 10, like 10 minutes left.
Fun for TV. Not when it comes to college tuition. With University of Phoenix's tuition guarantee,
I'll start doing my homework. So just looking at Prompt 5, which
no surprises. Learn more at phoenix.edu.
Okay, so here the question states So let me see. Let A and B prove that if A is if A is a subset of B, then oh wait, I already did this. Yeah, I'm stupid. Sorry. Let's look at 5. So it states that 5A, if A and B is 0, then A equals A union B minus B. Okay. So to prove this, understand that A and B is equal to the sets X. I believe are integers or for numbers. I don't really know. It doesn't really matter. No. I forgot. It doesn't even have to be anything actually. Equals to sets such that is an element of A and X is element of B. This is true. So if A and B is 0, A union B is X such that sorry, oops, or X. Now, since we know these two, A union B minus B is simply I believe it's X such that wait, I forgot what the minus means again. I know the set difference. I believe it's this one, right? The properties are annoying. And, alright, not and, okay. So this is the property where X is A or X and X. So I guess I'm factoring this out where it's the same as writing X. And we know that this is simply it's always false. Because this is I believe not tautology, the other one. Oh, okay. Okay, sorry. It is a contradiction. which is simply just elements of A. I wonder if I did that correctly. But I understand the logic. It's not necessarily hard, but let's look at B now. It's saying that A is does not equal B. So here, it's saying that A does not equal to B if and only if So let's first do this, I guess. Gotta prove this is not the empty set, not just zero empty set. So A does not equal B. So given two sets A and B, they don't equal each other. If if A does not equal B, then okay. So like I'm just gonna assume like if A does equal B, then this will be the empty set because this would removing every single element of. Okay, I completely understand now. I guess to prove this, I guess we should first mention what A equals B means. It's basically a set where right? Oh, that means it's an and, right? And okay, so means that it means that sorry. Wait, this thing. So if A does not equal B, it means it does not. It does not necessarily mean that I don't think it means this. I kind of have to stop and think for a second.
We're not winning this round. My teammates are.
Of course, it's always fault. Meanwhile,
Um, This one's a bit of a hard one, I guess. I gotta take it on office hours. So the third one, this problem. Oh, this one's kind of. It's not this one. It's shown in the example, I believe. So, to prove this one is simply, we know that. Oops, this is A, right? So, we know that here implies that no, hold on. Am I doing this correctly? Yeah, this is true so far. So, remember we're trying to prove I guess my inference right now is to how do we show that this now is also I guess which I guess you can say this, correct? And you can oops. And you can also prove that X is also which is also a subset of B. And because well, you don't need that. Yeah. Oh, this doesn't necessarily prove that oh no. So here this is essentially so we know that A and C, right? Here. But this does not necessarily prove
I just said.
Here it is.
I'm so sorry. This.
So that's it? Wait, this is it. This is literally it. So the little issue was that oh, I kind of understand. So because no, it probably should be like this. The last one here, I believe. Oh, this one. I think she showed this with Wait, I thought she said this is true, which is funny.
Book? list everything out, and then you don't have to.
No, it's not this lecture. I believe this one.
Oh, you're right. Sorry.
So, where's it?
Relation doesn't make matrix, if you know.
Here. Oh, no, no, no. It's not, okay, so it's not equal. It's, yeah, here. It's, their subset. I guess problem 6 is the question, I'm kind of wondering what the answer is to. Over here, 6A, I suppose. Like, think of a counterexample. Let me see. So, counterexample of this expression right here. So, subset. Okay, wait, let me think for a second. So, let's say like A and B are does it. So let's just give it like A 1 2 and then B equals 3 4, right? So P of A is I believe if you were to kind of, so remember empty set 1 2 and then 1 2. So P of B, I believe, is the same thing. Empty set 3 4 3 and 4, and A minus B is well, it's just sorry, A minus B is just A for the most part, right? 1 2. So P A minus B here is simply just P of A, right? It's just P of A. P A minus P, sorry, P of B is the P A minus the set 0 set not. Wait, no, it's the same thing actually. Same thing. Because yeah, PA minus B. Wait, no, it's not. It's not the same thing. because A minus B is simply like the empty set is still here, but empty set, but the it's not the no, it's not the same thing. So again, problem 7. This one is it looks just more of inside knowledge. Let's do the summary. It didn't take so long. Let's do, I guess, um third lecture. No, not third lecture. I'm sorry. I mean, summary. I believe this is what 3 point what 3.5. Wait, I kind of wonder, should I like review this and go to the gym tomorrow and go to the gym as well? Cause I can just do this and read this at the gym, I believe. Because it shouldn't really be it shouldn't take me sitting down and doing this, I suppose. But today, I think I'm just gonna be.
To set the stage. From getting
Yeah. Yeah, cause yeah, I don't think I'm gonna be writing anything, cause my reflection video is not going to cover. So I'll end it here. It seems. I got a protein shake, go to gym, maybe do a workout. I don't really know. Hope, cause I don't want to end my day off in a negative attitude. I asked like in a stressful way. I mean, so I have to. I have to. I guess take it out on something. Yeah, 3-hour video. It's good.